new quantum theory based on these Schrodinger waves. So this is what I was talking about earlier, because he is the one who gave us the particle nature of light and the photoelectric effect. That is considered the old quantum mechanics. Today, when high school chemistry students have to memorize the funny football-shaped orbitals that surround the nucleus with strange labels and quantum numbers, they're actually memorizing the solutions to the Schrodinger wave equation. The breakthroughs in quantum physics now accelerated enormously, realizing that the Schrodinger equation did not incorporate relativity. Just 2 years later, Dirac generalized the Schrodinger equation to a fully relativistic theory of electrons, and once again, the world of physics was dazzled. So Schrodinger did not incorporate relativity in his equations because, he was already doing something new. He was writing down the equations for matter waves, for the atom, for a particle, and there was some, math and figuring things out to do there already, and nobody had really attempted to write down equations for a particle in the sense of like this wave equation for a particle before, right? Because people hadn't really this wave particle duality thing was not as accepted, or was not even a thing before photoelectric effect, probably. So at this point, people are being brave. People are asking good questions with regard to the duality of things. They're asking, well, if light can have a particle nature, can matter have a wave nature? This is quite fundamental. This is quite different from how people used to think. And so to then take that further and write down the wave equation for a particle, that's quite something. And that's what Schrodinger had done. So this is the big contribution of Schrodinger and his equations. Hi, Aditya. Good night. Hello. And then here comes Dirac, and he is saying, well, you could even incorporate relativity into these equations and make them into relativistic Schrodinger equations for matter. Why not? Hi, Aditya from India. Very nice. Thank you for joining. Welcome, welcome. So realizing that the Schrodinger equation did not incorporate relativity, just 2 years later, Dirac generalized the Schrodinger equation to a fully relativistic theory of electrons, and once again, the world of physics was dazzled. While Schrodinger's celebrated equation was non-relativistic and only applied to electrons moving at slow velocities compared to light. So if the electrons that Schrodinger is writing down the equations for move at a slow speed compared to light, then it's okay to write them down as non-relativistic. But if they were to have speeds that are close to the speed of light, then you might want to write them down as relativistic. And in general, if you were going to make them more general anyways, then relativistic is the more general form of any of these equations. So that's why Dirac took it a step forward, and that's a very important step forward because, of course, it makes the math more complicated. So if somebody wants to sit down and do it, then here's Baji, then why not, right? So that's what Dirac was doing here. Hi, Kayla. Kayla Cauldron's sister Kimmy has joined the chat. I'm back. Oh, very nice. So this is the work that Dirac is now going to do, which is to take Schrodinger's equation forward and further and make them relativistic. So Dirac's electrons obeyed the full Einstein symmetry. Furthermore, Dirac's equation could automatically explain some obscure properties of the electron, including something called spin. So when he introduced relativistic nature to these equations, that is where you get something called spin, which is a fundamental property in quantum mechanics of particles. I missed you so much. Aww, missed you too. We're talking about physics, but thank you so much for joining and have fun with us. Here's Fuji and here's Baji.